We are going to finish up those examples from partial fractals, so let's jump into it. Yeah?
First thing I did was I did long division.
Okay. What did you end up with?
I got 1 plus x plus 5 over 4x squared minus 4x minus 3.
Now, you could do long division. You could also do that trick where you essentially just get the denominator in the numerator. Of course, you have minus 4x. To get back to the minus 3x, you have to add x. You have a minus 3. To get back to the plus 2, you need to add 5. And so you split it up here and there, and you'll get to here quicker than long division would have gotten you. But that is still correct. Then what?
And then I separated the integral to two separate integrals, integral of 1 and the integral of x plus 5 over 4x squared minus 4x minus 3. I focused on the fraction. I used I did it like the fraction, I separated it. I factored out the denominator.
What did you get?
I got 2x plus 1 and 2x minus 3. And then from there I did the partial fraction.
Okay.
And the two partial fractions I got were a over 2x plus 1 and b over 2x minus 3.
Okay. And what answer did you ultimately end up with?
The value of a I got was 4.5 over negative 4.
What is it as a fraction? It's 9 over 2.
Yeah, 9 over 2.
So I don't. Your a is the guy on top of this.
Yeah.
Right. So you could also figure out the answer by covering that up and plugging in minus a half. Got 9 over 2. And for this one?
I think it was, I didn't simplify, I got 13 over 2 over 4. So what is that?
13 over 2 over 4?
Yeah.
That's 13 over 8. Does everyone agree? You guys got those numbers? Yes? No? Yes? No?
Yeah.
What, you agree?
Did I mess up?
At this point, you should be able to integrate. What's gonna happen?
Well, the integral of 1 just act.
Let's integral this. What'd you guys get? Yeah.
ln 2x plus 1 times 9 over 2.
No, something's off. Yeah, the integral of 1 over 2x plus 1. Forget the 9 over 2. What is that?
Absolutely. 1 half times ln.
1/2 times ln of the absolute value of 2x plus 1, because you need a substitution. U equals 2x plus 1, your du would be 2 dx, you divide out the 2. So it's actually 9 over 4 ln of 2x plus 1. And this one, for similar reasons, it's going to be 13 over 16 of ln of 2x minus 3. Let's see. So that is that one. Yeah.
So you could do that all the time. That's a trick. You could just divide that over, put that like.
If your substitution is going, if the derivative of your substitution is a constant, then yes, you can divide by the constant. only in the case that your derivative is a constant. So, yeah, in general, ax plus b dx, it's 1 over a ln of ax plus b. That's in general. But that's from like an easy substitution. U equals ax plus b. Of course, your a is not equal to 0. Try B. B was,
It was square root of x over x minus 4.
yeah,
So the first thing I did was I squared it, and I got x over x minus 4 squared.
you cannot do that. Illegal.
Really?
Yes. Like if I give you, okay, I give you $5. You can just randomly square it. You owe me 25. You can't randomly square something. You change the value of it. So no, not allowed. If you have an equation, you can square both sides of the equation. If like you have something, you can't just randomly, oh, I'm gonna square it because I don't like the square root. It doesn't work. Illegal. Other ideas? Yeah?
Times root of x both sides.
Multiply and divide by radical x.
Yes.
Okay. How does that help?
Wouldn't that make it harder?
What did you do after that? I mean, that would be this. How do you deal with that? What did you guys try?
Couldn't you do a over x minus 4?
No. Why not?
Because it has to be 1 degree less, so that wouldn't make sense.
No, it's not why it doesn't make sense.
Like the a has to be 1 degree lower than the denominator, so you can't use a, you'd have to use a different value.
What does partial fractions apply to? What kind of functions can we use it on?
Proper.
Huh?
Rational.
Not just rational.
Rational.
Proper rational functions. That square root of x throws a wrench into the plan. We cannot apply partial fractions as is.
Use substitute, no.
Substitution. The radical is making it complicated. Right? Or you can do u squared is equal to x. My 2u du is equal to dx. So go in and plug all these guys in. Of course, my x is going to be u squared. My radical x is going to be u. My x minus 4, that's just going to be u squared minus 4. And my dx is going to be 2u du. Remember, you're training grasshoppers. You should be thinking substitution before you think of anything more complicated.
Okay.
Right?
Now you can break it.
This is a complicated thing. Like, what am I going to do with that radical x? Substitution. Now, these u's are going to cancel. How do I deal with this integral? Yeah.
You could expand the denominator to u plus 2u minus 2.
Why?
It's the difference of 2 squares.
You can?
And then from there you can do partial fraction.
No.
Can I just divide it?
First you have to make it proper.
Right, it's not proper. You can't jump into partial fractions. Step 0 or step 1 in partial fractions, you need to make sure it's proper. That's not proper. How do I get it proper? Yeah.
Minus 4 plus 4 and then not numerator.
You can do
You
it.
get
Minus
2.
4 plus 4.
The integral of
You'll get 1 plus 1 over u squared minus 4.
And you can do fraction.
And at this point is where you're gonna start worrying about difference of squares and all that. So this, you're obviously gonna wanna split into that. How do I find the numerators?
They cover up.
Okay. What
So
would you
u
get?
equals 2,
1/4.
and yeah,
So you cover up that, plug in u equals 2,
so it's 1.7 u equals 2.
u equals minus 2, cover that up, plug in minus 2. Integral of 1 here? U, right? Not x. This is just going to be a quarter ln of u minus 2 minus a quarter ln of u plus 2. And my u was radical x. And that's the answer. Integral C. Yeah?
Why is minus 4 plus 1?
Plus 4. I don't know why I put plus 1. That changes things? Yes.
Just like different answer which
So
come up.
now, if I cover that up and plug in 2, it's just 1
1 negative 1.
and negative 1. Just 1. So, missing. What is this one? How do you do this? Huh?
U equals e to the x.
du is going to be e to the x dx, and so this is going to give us 1 over u squared plus 1 times u minus 1 du. How do you do with that?
Partial fraction.
You know the value over u minus 1 is going to be 1.
Yeah, so this here is going to be au plus b, and over here,
1/2.
this is going to be, if I cover that up and plug in u equals 1, I get a half. So now I'm going to work on the partial fractions here. So I want 1 over u squared plus 1 times u minus 1 to be equal to au plus b over u squared plus 1. Should be plus a half. Plus a half over u minus 1. Now, of course, you multiply both sides by the denominator on the left, you would end up with 1 is equal to au plus b times u minus 1 plus 1 half times u squared plus 1. Now, how do you want to get to a and b? We have options, but what do you want to try?
Can you make u? Trying to see. Can you first make u 1?
Okay, so you want to do the plug-in convenient value, so if u equals 0, we would get 1 equals, your u is 0, so this is going to become minus b. And if your u equals 0, that's going to be plus 1 half. So this means that your b is equal to 1/2 minus 1 equals minus 1/2. And you can plug in some other random value.
1.
Negative.
U equals 1 is already accounted for because that's what we used to figure this guy out.
2.
So, and even -1 might also work. I guess you could plug in U equals 2. Doesn't really matter. It's small enough. So here we'd have 1 equals, if U equals 2, you would have 2a plus b times 1 plus U equals 2. This here is 5. This is plus 5 over 2. So 2a is going to be equal to 1 minus 5 over 2 plus 1 over 2. So that's minus 4 over 2, which is minus 2. 1 minus 2 is minus 1. So this means your a is also negative 1/2. So going back, plugging that in, we have negative 1/2 u plus everyone's like 1/2. Let's just factor out 1/2, make this look a little nicer. Factoring out 1/2, maybe even factoring out negative 1/2, I would end up with u plus 1 over u squared plus 1 minus 1 over u minus 1. Everyone agrees with these numbers? You guys got those? Minus 1/2, minus 1/2. And how would we deal with, well, this one, of course, that's going to be ln of absolute value u minus 1. How do you deal with this one?
You use U substitute? No. Okay, never mind.
Yeah, you could, yeah.
Okay, what would the substitution be? Let's say t. T equals what?
U squared
Huh?
plus 1. T equals U squared plus 1.
U squared plus 1, your du is going to, your dt is going to be 2u du, you're going to get this u. What do you do with that plus 1?
You just leave it there.
Not how substitution works.
Do you use trig substitute? No, that'll be too complicated.
Low division?
Yeah, way over. What?
Low division?
Don't need long division. Power on top is smaller than the power on the bottom.
Would you do another partial fraction?
How you can't factor the denominator. So my substitution takes care of this guy, leaves off the 1.
Can you separate it?
Separate
Yeah,
it.
subtract 1.
Substitution applied here. What is this?
That is
10.
10, arc 10.
Arc 10 of u would be the integral, and that's going to be your ln. Here it's going to be a substitution where the derivative is going to be 2u du, so you're going to divide out 1/2. So this is going to be 1/2 ln of u squared plus 1, plus this is going to be arc 10 of u minus ln of u minus 1. So that's 1/2. Our u was e to the x. ln of e to the 2x plus 1 plus tan inverse of e to the x minus ln of e to the x minus 1 plus c. Technically you don't need the absolute values here, but it's not wrong to keep them, so I'm going to keep them. Because there are situations where if you forget them, you're wrong. Yeah.
How do you get the half again? Not the first half, the half inside.
Substitution. U equal t. T equals your u squared plus 1. Your dt is going to be 2u du, which means that 1/2 dt is going to give you the du. That 1/2 is the 1/2. So that's that one. You guys are getting better, but you need to speed things up. Like, your guesses aren't as outlandish as they were like 2 weeks ago. So that's good. But still need to be a little bit more on point. And I suspect one of the reasons why some of you are not on point is because you actually don't do the problems that I leave you to do. You wait for me to do them on the board. Whenever I leave you examples to do, actually try them on your own. And then try more examples than I leave you to do, just to make sure it's solidified. That's how you're going to build up the XP points. A lot of things come down to experience. It's not that you need to be smarter, you need a higher IQ, you need more experience. Yeah.
It's negative 1/2, right?
Is it negative? Where?
Yeah.
You miss the negative sign.
Where?
When you separate it,
Oh, here?
yeah.
I had it there, but I just dropped it, yeah. So. What's the next example? Are we gonna get through it all? Let's try. What is this? D. Cosine x. You're gonna do that one. Ideas? Yeah.
Can you do substitution? U equals sine x.
Okay, how do you deal with that?
Then you do partial fractions.
Mm-hmm. So it's going to be over u and u minus 1. What are the coefficients?
A and B.
Mm-hmm. What are a and b? Hmm?
Negative 1
Negative 1.
Negative 1.
and 1.
Oh.
Okay, integral this.
That'll be ln. No, wait, sorry.
Minus ln of absolute value. This one?
Plus ln of absolute value minus 1.
And RU was the sine function, so it's minus ln of sine of x plus ln of the sine of x minus 1. Now, we actually did this example before. Last time we did it, we used trig substitution. So this time around, no trig sub. Do it without trig sub. Right? So for an alternative way to look at this integral. And of course, whatever we do here, you can go back and you can compare it to when we did it with trig sub. And you can choose which method you would have liked more. And then you just know for the future, you have the experience of knowing, in a situation like this, I'm going to choose to do trig sub, or I'm going to choose to do something else. How do you do this without a trig sub? Yeah.
You could use u equals 1 plus x squared.
Right, but we're gonna be left with a radical here, which that's gonna end up like 3 examples ago. It's actually gonna look quite similar to 3 examples ago. So, knowing that I'm going to want to get rid of the radical in the end, I'm just going to do a u squared substitution at the beginning. So now I never have to worry about the radical. 2u du is going to be 2x dx. So u du is going to be x dx. You could also notice, to get that x dx in there, you might notice, well, we don't have an x dx. Yes, we do. X over x. You can do that little trick. So now you go and you plug everything in. So the top, the entire radical just becomes a u over. Here in the denominator we now have x squared. X squared I can solve for here, that's u squared minus 1 times. So that takes care of this. Now I'm going to have that x dx, that is just going to be u du. So this actually simplifies into the integral of u squared over u squared minus 1. That is the guy we actually dealt with earlier. So that is going to, well, very similar to the guy we dealt with earlier. So here you just actually subtract 1, add 1. So that's going to be 1 plus 1 over u squared minus 1. So that's going to be u minus 1 times u plus 1. So put that into partial fractions. Plug in u equals 1, get a half. Plug in u equals minus 1, get minus a half. And our u was actually the radical of 1 plus x squared. So this is actually the radical of 1 plus x squared plus 1 half ln radical of 1 plus x squared minus 1 minus 1 half ln radical of 1 plus x squared plus 1. And you can compare this to the trig sub version of the solution. Personally, I prefer this way, but it's up to you. If you prefer the trig sub way, no problem at all. Just do it that way. That was neat. F.
Partial fractions.
Okay, how would you factor the denominator?
X plus 4x, or, oh, it's a cube.
It's a cube, yeah. Yeah?
X squared plus 4 times x minus 1.
X squared plus 4 times x minus 1. Does that actually work? X minus Yep. And what would you? So that's x squared plus 4, x minus 1, dx. Then what?
Use the power up method to get the
Wait, does that actually?
No,
That's
it
not
wouldn't
gonna work,
That wouldn't work.
because this here, this actually gives us an x squared, not an x, because you have the x there. Like you're thinking in squares. No, that's not gonna work. What else would you try? You guys remember how to factor polynomials more generally? Probably would have learned it in pre-calc. You may have seen it in Calc 1 now and then. Like the rational roots theorem, you guys remember that? Like how to use long division to figure out how to factor polynomials? No? Okay, make a note, look that up. 'Cause sometimes that's something that, in my head, when I'm writing tests, that's one of the things I'm assuming everyone knows how to do. It's actually not needed here though, because what if I made u this? What would du be?
2x plus 3.
3x squared plus 3.
And notice that 3 is a common term, I can factor that out. What do you notice?
It becomes
It's 3 times the numerator. So this whole integral is 1/3 the integral of 1 over u du. So it wasn't in partial fractions at all. It's just that, of course, whenever you teach a new method, students often forget about all previous methods, so every now and then I'll throw in an example to guys to remind you, you should be thinking substitution first, before anything else. It looks complicated, it doesn't matter how it looks. Substitution is always considered before doing anything else. So if you look at that and your first thought is partial fractions, you're not thinking correctly. Your first thought should always be, is it a basic rule? Can I simplify it? Can a substitution work? And in this case, the substitution did work. G's actually a nice one. I'd actually. I'll leave that guys to you here. But hint, in this case, we are going to want to factor the denominator. So remind yourselves how to do that. Let me know what you come up with tomorrow. Or unless anyone actually did this one. Okay, go home and work on it. I think, how can I factor the denominator? Look that up. Rational roots theorem, probably. So look up rational roots theorem to factor polynomials. Right. Do a Google search of that. You should find something useful. Push comes to shove, you can look at my Math 1000 lectures. I taught that in the class. Let's. Right. Let's talk about a different technique. We're going to talk about a different kind of substitution. So we learned about you have a regular substitution that you can tweak, make it a u squared substitution or u cubed substitution. We saw the trig substitutions. At some point I'll probably also tell you about some hyperbolic function substitutions, but right now I want to talk about a really cool one. It's called the Weierstrass substitution. here's where this substitution would actually apply. How do you know that you might want to actually think about this? It's that given, if you have an integral, say f of x dx, where your f of x is a rational trig function. What do I mean by rational trig function? Well, think rational function, but instead of x's, you have trig functions in places of all the x's, right? So it kind of looks like a polynomial, except instead of x's, you have trig functions, right? It'll look like a ratio of polynomials, but with trig functions in places of x. So I'll call that a rational trig function, right? So let's say I gave you the integral of some rational trig function. It turns out that often the substitution now first it's going to look a little weird, but we're going to do a substitution of u equals the tangent of x over 2. We're going to introduce a tangent function into this. And you might wonder, like, how is that going to actually help? But it's a very cool substitution. It's called the Weierstrass substitution. Let's actually get some things right off the bat. Now, with this substitution, what you're going to want to know what to create is things like sine and cosine. Once you can create a sine and cosine from this function, that's going to be useful because with sines and cosines you can create any other trig function you want, as well as you're going to need to know how do you actually change the dx if this is the case. So now if your u equals tangent of x over 2, what that means is that you can imagine that there is some right triangle where the angle is x over 2. And tangent is opposite over hypotenuse, opposite over adjacent. So that's going to be on this side, it's going to be the u. This side is going to be the 1. On this side, Pythagoras' theorem is going to tell you this is 1 plus u squared. This automatically means that the sine of x over 2 is opposite over hypotenuse. It also gives you that the cosine of x over 2 is adjacent over hypotenuse. Okay. Now what does that mean for the sine and cosine functions? This of course means that if I wanted to find what is the sine of x, right? So let's say there's a sine of x in this function. How would I calculate that? Well, I just think of this as sine of 2 times x over 2 and apply a double angle formula. This is 2 sine x over 2 cosine x over 2. And I know that my sine of x over 2 is this guy, my cosine of x over 2 is that guy, and I just multiply them, you would get 2u over 1 plus u squared. Let's actually copy that down here. I can continue by finding the cosine of x, and I would think of this as the cosine of 2 times x over 2, applying the double angle formula. This is going to be cosine squared of x over 2 minus sine squared of x over 2. That is going to be 1 over 1 plus u squared minus u over 1 plus u squared. And so that just gives you 1 minus u over 1 u squared. 1 minus u squared over 1 plus u squared. So with this substitution, you can replace all sines with that. You can replace all cosines with this. And of course, you can divide both of these to create a tangent. So your tangent is going to be this divided by that. The 1 plus u squareds are going to cancel. You're going to have 2u over 1 minus u squared. Also, what you will notice is that from here, I could actually solve for x. X would actually be, well, 2 tan inverse of u. And so you take the tan inverse of both sides and multiply by 2, which means I can actually take the derivative of both sides. The derivative of tan inverse is 1 over 1 plus u squared. And so I can change my dx to 2 over 1 plus u squared du. So we have this set of equations here from which we can construct any trig functions that we want from x's to u's. How is that useful? Let's actually do an example. Now first I'm going to do an example that there's another way to do it, and we'll probably do it the other way afterwards. But just to start off, let's do so there is a rational trig function. Here's something you can do. Apply our Weierstrass substitution. This automatically means that these guys take effect, which means everywhere I see a sine function, sine x, I can replace it with this. And where I see the dx, I can replace it with this. Now what you'll notice we can do is I can just multiply across. That's going to be a 2 on top. Multiply this in, that's going to be 1 plus u squared. Multiply this in, that's going to be 2u. So that's u squared plus 2u plus 1. That actually simplifies. That is u plus 1 all squared. And that we know how to integrate. That's actually minus 1 over u plus 1. Right. Technically you do a substitution, but it essentially comes down to add 1 to the power, divide by the new power, plus c. And that is going to be our integral. Minus 2 divided by, our u is tangent x over 2, plus 1, plus c. And that's our answer. Try to do this without Weierstrass. As well as try to do the other problem I mentioned, so you have to review rational roots theorem, all that good stuff. And just in general, just go over integration as we've done it before. We'll do some more on the Weierstrass substitution next time. But it's a way that you can start out with trig functions, but you turn it into rational functions. It's almost like the reverse of a trig substitution. A trig substitution brings you from a situation like this to a situation like that. But the Weierstrass goes the opposite. Sometimes you have trig functions, but you don't want them. You want to go to rational functions. You use a Weierstrass substitution to accomplish this. And oftentimes, it will be nicer. We'll stop there for now, and we'll pick up. So the quiz today is on partial fractions, so more on what we were doing last week as well as earlier today. See you guys tomorrow.